Given the results of an experimental lab involving bar magnets and a magnetometer, create a computational model that better approximates the magnetic field of a bar magnet. Understand and discuss magnetic field and its relationship to the magnetic dipole moment for bar magnets. For the fundamentals of this lab, there are three major topics. Given a bar magnet, the magnetic field vector from an observation point on the axis is given by B parallel. We can also use the distance-dependent equation for the magnetic field of a bar magnet, which is a constant k times a position r to some n value. It's important to note that we can graph the relationship between the magnetic field of the bar magnet and a position using the natural log of this equation. Finally, we can also use a derived version of the Biot-Savart law, which gives us the magnetic field of a dipole at some point in space. We should note that the magnetic dipole moment of a bar magnet travels from the south pole to the north pole of that magnet. And if we are given more than one source of magnetic field, then we can use superposition to find the net magnetic field at that position. For the design of the experimental portion of this lab, we first measured the on-axis magnetic field of a bar magnet using a magnetometer from our phone. We found the location of the magnetometer on the X and Y axis, and then used different distances to create a graph that relates magnetic field to position. We also measured the off-axis magnetic field of that bar magnet at some distance d perpendicular. Here's an Excel spreadsheet representing the data I found, as well as the graph of the magnetic field relationship to the position. I was able to find n and k by setting n as the slope and the natural log of k as the intercept of the graph. It's important to note that we had to correct for the Earth's magnetic field for the off-axis, but for on-axis we accounted for this by aligning the axis with the Earth's magnetic field. By setting the two equations for magnetic field of a bar magnet equal to each other, I was able to find that the magnetic dipole moment is equal to 0.22 amperes times meter squared. And as a preview, I found that this experimental data was off by about a power of 10, but it's useful in understanding that magnetic field decreases with distance. At the start of our experiment, the bar magnet is some distance r away from the observation location, and the Earth's magnetic field is in effect. The system is the bar magnet, and their surroundings include the observation location and the Earth. For our assumptions, we assume that the r dependency cancels out when we solve for mu. This is how it would be in an ideal magnetic dipole, as we assume the bar magnet is. We also know that the Earth's magnetic field is in effect, and has a large effect especially when the bar magnet is far from the observation location. And for the code model, we assume that our mu value from the experimental lab is correct. First, we inputted the magnetic constant, and then modeled the magnet as a cylinder object, with our mu value as its magnetic dipole moment. We then used the Biot-Savart law to create our function for magnetic field, and solve for the magnetic field at distances on the axis, off the axis, and at 45 degrees. We modeled these magnetic field vectors as arrows, and here is our result. Comparing the experimental results with the computational results, we find that the experimental results are off by a factor of 10, and we know these errors are because the experimental lab is hardly accurate. The magnetometer I used was from a phone app, so the mu value I inputted into my computational model was likely inaccurate as well, meaning the coding results aren't accurate either, though they do correctly model the magnetic field of a bar magnet if that magnet had the given mu value. Now, what if we hadn't accounted for the Earth's magnetic field originally? Well, the Earth's magnetic field has a weak but non-zero effect on the calculations. We saw this in the experimental data for the off-axis field. My resultant By was approximately 7.6 e to the negative 5 teslas, but the corrected value was 2.9 e to the negative 5 teslas. This value, though off by a factor of 10 is more accurate compared to the glow script value of 2.6 e to the negative 6 teslas. So the Earth's magnetic field does skew the results, especially when the distance from the bar magnet is large. And what if we were to stick two magnets together end to end? Well, the resultant magnetic field would have the same dipole moment direction, but the magnitude of the magnetic field will increase. However, it will not double due to superposition.